Okay, hey everybody. I hope this works and I hope you can hear me. I'll just wait for the confirmation on my video stream and yeah, and we can go. Everything works, perfect. So hello everyone, good evening, and sorry for starting late today. I actually had a meeting which I needed to attend, and therefore I moved the stream 1 hour later. I didn't want to cancel it like the second week in a row. I'll try to actually make these every week, and yeah, and last week I was like going on a vacation next day, so yeah, I ended up canceling anyway. So I didn't want to do the same today. Anyway, so today we'll be doing. Oh, actually, this thing is incorrect. I need to fix it. Today we'll be doing basics of heap exploitation, which means basically I'll show you how. So it's like this. I've done some heap exploitation in the past. Not a lot. I don't know, maybe 5 to 7 exploits ranging from 200 points on the CTF scale to 500 points. But it's like this. I don't know the usual tricks you use when exploiting heap stuff. Now, but I do have a rather good understanding on how low-level programs work, how the CPU works, how the operating system works, how some algorithmical stuff behind heap works. Therefore, even without knowing the usual tricks on how do you exploit, I don't know, double free and so on, I was able to figure out how to write a given exploit anyway, just by looking at like what's the interaction between my overflowing bytes and the CPU, the code that the CPU executes. So yeah, that being said, doing it this way isn't really efficient as, well, you just basically, instead of using a well-known trick, you need to relearn every time the stuff that you want to exploit. So there's like an offline CTF coming in 2 weeks or 3 weeks. That's the Insomni hack offline. Well, not really finals because it's an open CTF and usually quite a lot of teams attend. And our team, Dragon Sector, is also going to attend, so I decided that it's finally time to learn the standard tricks of exploiting heap. Now, I need to start with something really basic, which is get to learn how the heap works. And this is actually not said correctly, because there are a couple of different heap implementations, and like, for example, on Linux you usually use the one which is in glibc, but not always. A couple of episodes ago I showed you an exploit for exploiting GE malloc heap implementation, which is different from the usual thing you have in glibc. Then on Windows you have a totally different heap implementation, and depending on the Windows version, that also changes. They do some improvements in it. So in the end, heap exploitation boils down to knowing how the heap is implementing, and that's probably will be the thing I will be focusing on today, is getting to know how how the heap on glibc in Linux is implemented. Maybe I'll try to compare it with Windows heap, and start from there. Now, okay, before I get further, I need to fix the topic here. Anyway, if you have any questions today, then feel free to ask. Just like grab this guy on IRC or on YouTube and ask him a question, and he will pass it to me. That's basically how it works, and thank you, KrzaQ, for actually helping me today. Now, yeah, so if you are wondering how does my bottom thing look like, it's a browser plugin, so it's Chrome, basically Chrome running in as a plugin for open broadcast software, which I'm using. Okay, basics of heap exploitation. That's how it is. Now I need to reload it. Okay, now it should be fine. But before I get there, some news, and there was actually a lot of interesting stuff happening in the last 2 weeks when I was not streaming. So first of all, where's my browser? Okay. First of all, sad news, Chris Kaspersky passed a couple of days ago. Do not confuse the person with Eugene Kaspersky, which is related to the antivirus company. Chris Kaspersky was actually a reverse engineer as well, and a security researcher. If you remember the good old days of openrce.org, you might recall him from there. He had the nickname Nezumi. He also is the author of, this book. I actually have a Polish copy of it. In English it was called Hackers Disassembly Uncovered, if I remember correctly. You can still find the book online, because he published the first edition for free for everyone to use. And this is one of the books I actually learned from back in the old days when I was learning reverse engineering, and he was a great guy. I also quoted him a couple of times and his research and on different presentations. So it's a big loss for the scene, and that's really sad news. Yeah. Moving forward, again, thank you to KrzaQ for being the moderator today. And yeah, if you have any questions, just ping him. And you can see his blog at dev.krzaQ.cc. KrzaQ is actually how you pronounce it. I know that if you're an English speaker, it doesn't look like the way you should pronounce it, but that's actually the way it is. Now, Life Overflow isn't sleeping. Life Overflow is publishing new videos, so be sure to check out his YouTube channel. It's, basically www.youtube.com/lifeoverflowctf. And if you're into security and CTFs, you totally should check it out. Now, as you probably heard, SHA1 is broken, and it's like, the scene in Harry Potter where Lord Voldemort says, like, Harry Potter is dead. I can say, like, SHA1 is dead. What happened is that actually a couple of people, some from Google, some from outside of Google, decided that they have a good implementation of something that can lead to a collision, and after some CPU time put into it, they generated two PDFs with the same hash but with different content. The content was actually really close, with just the background differed, but it did differ, which means that it's the first proof of SHA1 being of a collision which was created on purpose. Actually, I recommend the paper. It's really fun. And one of the guys involved was, by the way, Anja Albertini, which you might recall from PE 101 and other binary file format posters. So that's pretty awesome. Now, it seems somebody said, hold my beer and watch this, and next day we got a Cloudflare incident of a memory leak bug, which they basically had a HTTP parser, and Tavis or Monody from Project Zero from Google found out, I think by accident. Read the bug from Project Zero, it's actually published. He found out that, hey, at the end, when you download some pages from Cloudflare, at the end you actually get some random data, and it contains funny stuff. Some stuff is sensitive, and it turned out that they were leaking like a lot of random data from memory left, right, and center, which made this probably the biggest incident like in CDNs for a long time. Well, that's pretty awesome stuff, and also props to Tavis for spotting it, because it was out there, just somebody needed to spot it, and it turned out to be Tavis. Moving to this week, and we have like a WikiLeaks publishing CIA documents on exploitation and malware and so on, and basically check it out. It's they have quite a lot of interesting stuff there on like recommendation how to write malware so it's not detected, what you should obfuscate, and so on. Some exploit, like what they have, some ways of keeping persistence. Quite a lot of documents were published, and probably there's already some analysis on the internet. So yeah, fun times. Speaking of fun times, Yuru is recently publishing ways to crash Windows. Like local DOS is nothing severe, but it seems he has a plan of publishing one per week, and he started with some weird Win32k functions. Then the second post was about another weird Win32k syscall, but this was an interesting one, and you should read it if you're into bugs which are related to how the compiler, a C++ or a C compiler, generates code. And the compiler didn't do anything wrong in terms of how the C++ and C standard go, yet due to the way it worked, due to the way it did reordering, it caused a bug. Although it didn't really cause the bug, it's an interesting case. Totally check it out. And the newest one is an like anti-duplicate token. It's like, of all places, is one of the most basic APIs, I would say. We don't use it too much, but it's like one of the basic APIs anyway. So that's interesting. Cool. So yeah. So back to heap exploitation then. As I said, I didn't play too much, but I did play a little with it. And one story I wanted to tell you is totally not related to modern heap exploitation, but there was a task called DOS Fun for You on DEF CON qualifiers in 2014. The task was for double 500 points, meaning there were 2 stages and each stage was for 500 points, and it was deserved. Like, this task was totally worth 500 points. It's not like it was super easy and somebody should like just gave it 500 points. No, it was hard. We actually spent with Redford, which one of the vice captains from Dragon Sector, 20 hours reverse engineering it, and mostly because it wasn't a Windows binary, it wasn't a Linux binary, it was a Unreal Mode DOS binary. An Unreal Mode, so it's like this, you know probably that there's a real mode in CPU where you have 16-bit code and the segments are like really funny, as in you have basically blocks of segments just one after the other addressing the first megabyte of memory, right? Now, then you have protected mode, which is virtual memory, and you can place segments wherever you like in memory, but we don't do it. We usually use so-called flat mode in protected mode, which means that the segments always describe memory from 0 to, well, the end of memory. Now, and there is, of course, like the 64-bit mode, the long mode, and like compatibility modes, and so on. Now, there's also something which is called the Unreal mode, and it's something, when you boot your PC, the CPU is in Unreal mode. And it works in a way that it's 16-bit code, and there is no virtual memory whatsoever, but you can describe the segments in the same way as you do in protected mode, which means you do not have to follow the standard real mode scheme of segments, and instead you can say like, oh, this segment like describes this area of RAM, and another segment describes this area of RAM, and there is yet another segment which actually describes the same area of RAM but with different access, like with, for example, executable access instead of read-write access, right? And this is the mode they used for this challenge. There was an application, and that was also heap exploitation. Now, that was pretty funny. I'm going to show you a piece of the code. At least I want to show it to you. I have it somewhere. Here it is. So it's a piece of the code from the challenge. You didn't get the C code. I actually got it from Lightning, which is the creator of this challenge. This challenge was totally awesome, and full respect for him for writing it. Now, it was malloc to allocate memory, right? And the code was like this. This is a simplification. Basically, if 3 was non-zero, then you could basically allocate a segment, allocate some piece of memory, grabbing it from the free list. Whereas usually in heap implementations, there's something called like a recently freed memory chunks or memory blocks. And when you free something, it just goes to that list. And when you allocate something of a similar size, then you grab it from the list, so you don't have to, you know, grab it from the normal heap. It's just faster this way. And this was a similar implementation. And then you return it as a segment. Now the fun part here is that this is a far pointer. And if you're not programming if you're not programming in 16-bit mode, then you probably don't know what a far pointer is, or maybe you know. So a far pointer is basically a pointer which has two parts to it. The first one is the segment, and the second one is the offset in the segment. Usually, when you think of pointers, you only think about the offset. You never think about the segment itself. So that's the like distinction between a normal pointer and a far pointer. And then you have this. And you'd think, okay, this is setting it to null, right? This is like, yeah, similar to null, like null is 0 anyway, as we know. Now, it actually isn't. this actually what this does, what this line does, and what the what is surprising is this line sets the offset to 0, but it didn't initialize the segment at all. So it didn't initialize the segment part. Therefore, the segment part was uninitialized memory taken from the stack. And yeah, and you could basically here you could set the memory on the stack using some other methods for this to pass, basically for this to not pass, and you got basically to say which area of memory you want to allocate, and you can, for example, what we did is we pointed to a data segment describing the same area of memory of a code segment for the program, and we've overwritten the program code. And the funny part is that this was not an intended bug, it was an unintended bug because the author of the task assumed, and I totally don't blame him, I would assume the same thing, he assumed that this also clears the segment part. So yeah, if you are programming in Unreal mode, you have to better be careful of this. Probably what should have been done here is one should use this macro instead and put it like 0 here and do something like this. mkfp is like make far pointer, and this would be correct. It would initialize correctly both sides. Otherwise, it just initialized the segment. So yeah, so this is my experience with Heap. As you can see, this is totally not what what is used currently, right? And on like Linux exploitation and so on. So what I ended up doing a couple of weeks ago is actually starting to Google for Heap related information, and there are some pages that I found, for example, and glibc, on glibc Wikipedia, I found overview of malloc and how malloc works. I didn't finish reading it, in all honesty, but I read like half through it, and I'll actually focus on this document today. KrzaQ should pass you a link in a second. Then I also found understanding glib malloc from exploitfun.wordpress.com, and then there's some. This is actually an awesome collection on Shellfish. If you go to shellfish/how-to-heap, then you get it's a repository of, well, first of all, it's a repository of techniques, and second of all, it also showcases how malloc works in some scenarios, and how free works, and how you can massage the heap and do heap feng shui, so-called. That actually means calling malloc and free in a controlled way with a controlled values in case of malloc allocations to actually get the heap in a state you want before you actually proceed with the exploitation. Yeah, and they kinda hint at some of that here. Then there is on SlideShare, there is a presentation, House of Einherjar. I'm not sure if I actually, or maybe Einherjar? Yeah, I don't know. Yeah, which also looked interesting, and there's also a FRAC article on heap hacking, which KrzaQ will also pass you a link. So, so if you are on our chat, then you should get the whole set of links. Yeah, so what I'm going to do today is I'm going to basically show you how I'm going to approach learning the heap and looking what I'm going to look for, because I figured you're probably in the same position, like some of you, of course. Some of you might already know how to exploit heap, you might know all the techniques, and then you will be really bored on today's stream, but others might be beginners and might benefit, actually, what I figure is they might benefit from well, showing my approach on learning new stuff like this, right? And so yeah, so that's what I'm going to focus today. Then probably not today, but maybe next week or in 2 weeks or in some time, I'm going to find some heap challenge and do an exploitation on that. And I just need to, you know, find some time off stream to basically learn all the other things which I'm not going to show on the stream. So yeah, I'm going to keep this open. And oh, by the way, if you have any good links for like heap exploitation, then by all means pass them on IRC or YouTube channel, and yeah, like share them with whoever else is there. Cool. I see there are some questions. I do need to find my directory. Okay. Do you know where I can find good resources on format string attack? I'm trying to solve a challenge, but without much success. Okay, so the bad answer here is that, oh, on my Polish channel I had a tutorial on it, but it's in Polish, I'm sorry. Apart from that, I actually don't know. I learned Heap... I learned format string attacks like ages ago, and I have no idea where to find resources about it. That might be a good idea actually for another stream, like me showing you how to do a format string attack. That's actually something I actually feel really comfortable with doing. So if you like the idea, just post it in the comments under this video, and on the next before the next live stream, I'm going to like look through the comments, look which comments are the most like top voted on, and I'm going to pick a topic from there. If it's format string, then I'll just do a format string. So is this book, I guess is related to this book, which is Hackers Assembly Uncovered. Is this book still good for learning reverse engineering? That's another question. Kinda yes. So it's a little dated, but what it shows all the standard C and C++ structures and code patterns, and I mean small code patterns. How they look like an assembly, how to recognize them, and how to reverse engineer them. So that changed in the way how the compiler generates code, and obviously now we are in the 64-bit era, and the book is actually from the 32-bit era. But and there's like a whole chapter on IDA, which is still in text mode, so that's also dated. Apart from that, yeah, I would still recommend looking at it. Okay, so there are 2 more questions. I'm going to go from them, and then I'll jump straight into coding. From Christian, how a CTF organizer creates challenges. Does he create a challenge knowing how to solve it, or knowing the bug that he wants to reproduce? It's easier to create a CTF or to solve a CTF challenge. It's easier to create it. Now, how it's usually done is, yes, you have a bug in mind, like a specific bug and a specific steps that you want the person exploiting it to take in order to exploit the challenge. Now, what you usually have to do is you have to create an exploit yourself just to test the challenge, and just to make sure that it actually works, because it's pretty common that when you implement something complicated, it doesn't work the way you intended. So that's one thing, testing if it actually works. And the second thing is, it happens, especially in the more complicated challenges, that there are more bugs than the author of a challenge thought about. So he thought of, hey, you need to do this, and this to exploit it, but you actually find another bug and it seems to be easier or harder, but you still get the exploit. Like, it's CTF, right? Whatever works, works. So, for example, in the DOS fan for you, which I talked about briefly before, that was the case. Like, we found a bug which the author didn't intend to put there. And there's a video from PicoCTF on Vimeo about format strings. So Vimeo PicoCTF format. Let's see. Yeah, it's probably this one. Yeah, so I guess you can see the number here, but apart from that, just do what I did, is Vimeo PicoCTF format, and you'll find it as one of the top results. I'm going to paste it though on here and here. Yeah. Cool. So, no, I need to keep this open. I need this. I can close all the other stuff, I guess. Okay. So, what I'm going to do first is I'm going to basically write a super small program which just allocates stuff, and I'm going to so I'm going to be writing in C-ish, and by C-ish I mean maybe there will be some C++ there. Okay, yeah, and I'm going to just allocate some stuff, and then I'm going to start like snooping around, basically. Cool. So P is for pointer, obviously. I'm going to allocate, and I'm going to allocate let's say 1 byte of memory. Now, Usually, you cannot allocate 1 byte of memory, and I'm pretty sure, well, from what I've read already, this is the case here as well. What you can allocate is 1 byte of memory aligned to, or actually padded to, the minimal allocation size, which is usually around 8 bytes or 16 bytes. And it's basically because you, like in memory, especially on x86 but also on other architectures, you won't align addresses to the size of, for example, the pointer size. So aligned to 4 or aligned to 8 or aligned to 16. Therefore, if you allocate 1, you still probably want to just like pad it up to the size of 8, 16 or whatnot. And I actually kind of hope this will also reveal what's the allocation here. No, I actually need a Linux console here. Okay. DCC ASDFC. Let's see what happens. Okay, so it did the allocations. Now, what you can see already here, right, is that these addresses are pretty close. But this is not, and this is quite surprising, and I don't know why is that, but I might learn later on. Now, this already also showcases what I've said, right? I said that you cannot really allocate 1 byte of memory, and the reason I mentioned is the padding or the actually alignment of addresses and alignment of the sizes. The other reason is that usually when you allocate on a heap, you also need, you don't only allocate the 1 byte, you also allocate some structure which is before or after that chunk of memory. What you allocate, you usually call it a chunk of memory, and the structure is internal to the implementation of heap. Therefore, well, I said allocate a byte, but it actually padded it, for example, to 16 or to 8 bytes, and then it added the heap internal structure somewhere near it, and maybe it padded it again to some size, and therefore the difference here is actually 32 bits. So even though I allocated like 1 byte, it allocated 32. That's 32. I'm sorry, my handwriting is terrible, especially when I'm writing with a mouse. Yeah. So that's one thing. Now, reading this article, for example, what you might find out is that blah blah blah. All chunks are multiplies of 8 bytes, which basically means that, yeah, everything is aligned to 8 bytes. Now, a really interesting thing usually in heap is what happens. There are two interesting things. First of all is if I do, because this is the same page of memory, right? You can see it clearly, like this is the lower 3 nibbles. Nibbles are the hex digits, right? This is the offset on the virtual memory page. Each page is usually 4 kilobytes, and this is like the offset on that page. And everything from here is actually it's an address of the page. And you can see, like, this stuff is constant. Like, for all these lines, it's the same memory page. So we can assume that this is the same heap. It was taken from the same region of memory. Some implementations of malloc do it like this, that if you allocate 1 byte, or like small amounts of data, they will take it from one heap. Now, if you actually allocate a larger amount of data, like, I don't know, like 64 bytes or 256 bytes, they will grab it from a different area of memory. And yet again, if you allocate like a huge amount of memory, like for example 1 megabyte, they will just like say, no, we are not allocating this from heap. Instead, we are going directly to the operating system, doing a syscall, which is expensive, and asking the operating system to allocate you some memory directly, like basically assign you virtual pages, right? So for people basically not familiar with the mechanics of this, is like this, but you can ask, as a user mode program, you can ask the operating system only for pages of memory, and again, a page is 4 kilobytes usually. You can have larger pages, but let's assume for the sake of a discussion that the page is 4 kilobytes, right? And heaps like malloc are implemented because you don't want, if you want 1 byte, you don't want to allocate a whole page for it. And if you are creating, for example, a linked list of objects where each node of a linked list is a separate chunk, you don't want to be wasting space allocating a virtual page of memory for each of the nodes, because you are wasting like almost 4 kilobytes, right? You're just using, I don't know, like 16 bytes or something, but you allocated 4096 bytes, so you're wasting a lot of space. Therefore, therefore the heap is a way to separate, not separate, to split the virtual memory pages into smaller chunks, and to be able to allocate, tell the heap implementation that, hey, I want 1 byte, I want 16 bytes, and so on, and it will split the memory page into such chunks. And when it runs out of a virtual memory page, because it allocated, for example, only 1 page, then it will allocate another page, and it will split that. And if you free something, then it will say, hey, this chunk, this piece of a whole page is now free, and when you, what I already said, it goes to the so-called free list. And when you allocate again a chunk of a similar size, which is the same size or smaller, it will just grab that part of data. So the most simple implementation of heap is so-called dirty alloc, and it doesn't have any free. It just allocates linearly memory which you request, and when you are done, it just frees the memory pages. So what we can do here is we can do an strace, and we can check basically what mallocs are, what calls to the system requesting memory are done. So yeah, that's just mmap. Mmap is what is called to get the virtual memory page or pages from the operating system. Now, what you probably know anyway, on Windows it's called virtual alloc, by the way. Yeah, and this is like the library is still loaded, so this is not our stuff. Our stuff begins, I don't know if there's actually any stuff related to these mallocs, because it might just be in the area which was already allocated by libc or something. So what I'm going to do is I'm going to basically remove these, just comment them out. No, before I do that, I'm going to put this into log1. Now I'm going to do this, and I'm still going to keep printf. Why I'm going to keep printf is because what I want to find is I want to find how malloc actually interacts with the operating system. Does it request memory, a memory page, or maybe it doesn't request a memory page? And I know for a fact that printf does indeed request a memory page using mmap. That's because standard output is buffered, and by default on glibc level, therefore glibc needs to allocate some memory, and it does it using mmap. So if I would remove it, then one of these mmaps would be gone, and that would screw the results basically. Yeah, and now I can, no, I need to recompile it obviously. Yeah. Okay, and now I can diff it. Though I'm not going to use standard diff, I'm just going to use total commander and compare by content. Here we go. The addresses differ, obviously. Now, BRK is another interesting thing, because BRK is another way to get memory. BRK is change data segment size. It's like this, that when you have an ELF file at the end, there's a section basically which is used as heap, and BRK is a way to extend this section, and by extend this section I mean allocate virtual memory which lies just at the end of that section, and basically extend the section. So BRK might be a way that for malloc to actually get data, but it's too soon. glibc is not even loaded then. glibc is loaded here, so yeah, and BRK null. Now what is what? Okay, so this thing on the left is actually without the prints and without any allocations, and on the right is with allocations. And as you can see, it actually seems to be, no, that's not true. I wanted to say it seems to be getting the memory from using BRK, but on the left and the right it's the same thing. It actually seems that we can assume that the application starts with already some requesting, like just of from the get-go requesting some memory. But again, this is not the interesting part I wanted to check. What I wanted to check is I wanted to see a couple of allocations with increasing sizes, and where is the... I wanted to find out where is the boundary between it allocating... Maybe there are different heaps, and like for small chunks and for larger chunks, and I wanted to find the boundary. So what I'm going to do is I'm going to do a loop. And as you can see, I'm actually not going to bother with yeah, I'm not going to bother with cleaning memory for now. When you exit the process, you clean the memory anyway. Yeah. Let's see what happens. Okay. Now, what is expected is that, let me maybe put it in a text file, ASDF. ASDF is a perfect name for a text file, isn't it? What is expected is obviously for these addresses to increase, but what's not expected is for the pages to change too rapidly. If the page changes rapidly and not in a linear fashion, that usually means that, hey, it actually jumped to another area of memory where a different heap is put up for different sizes of memory. And if nothing like this happens, that usually means that this implementation of heap doesn't really have these mechanics in place, which is also a valid solution, I guess. Now, what you can find already interesting is that 0 for 0, if you want to allocate 0 memory, we don't get null, we get a valid address. And this is actually aligned to the C standard and C++ standard as well, which say that if you're allocating 0, you still need to return a proper pointer, which is non-null. So this is an implementation of it, I guess. Now, I guess what's interesting is what would happen when we would allocate multiple times 0. Would it return the same address, or would it maybe not return the same address, but return, like, still allocate, for example, 8 bytes for us anyway, regardless? We can check in a second. That's a good thing to check. So yeah, so let's get going. Here, as you can see, the addresses are increasing normally. This is basically the size, like 53, which is around, what is it? Is it around 40 hexadecimal, a little less, 30 something, plus the alignment, plus the header, like the malloc internal structures at the beginning of a chunk or at the end of a chunk. And yeah, it's just normal linear increases, nothing fancy here. Yeah. So yeah, my guess, and again it's a guess, I did not analyze the malloc for now, is that it actually has only one heap for all the sizes, and it uses the same area of memory to actually split it regardless of whether you request 1 byte or whether you request like 1 kilobyte of memory. Yeah, just a linear increase, so that's okay. Now what I wanted to check, right, is if I allocate multiple times 0, does it return the same address, which I'm going to do, just putting 0 here, and I'm going to, I guess, close this file, recompile it, and run again. No, it actually does allocation. It actually allocates like probably at least 10 bytes or 16 bytes for it. So that's another thing I need to remember when dealing with malloc, that allocation of 0 is actually a real allocation, and it's not an allocation of 0. It's an allocation of some padded amount of data. Cool. So I learned something. Now, what happens if I do really large allocations? But before I go there, I'm going to actually do a trace again on it, and I'm going to see if it actually, when I do malloc, if it actually calls the brk or does it call the mmap to allocate the memory. So yeah. Here we go. That's the right. Okay, where are you getting the memory from? No, seriously. As you can see it... Why does it... I don't get it. Because when I'm S-tracing it, right, it should show me something else than just writing this. But just... Where is the memory allocation here? Okay, that's weird. Let's do it like again. Recompiled, S-trace, and still only right. Where are my memory allocations? Now, this might not be super weird. Now, why am I saying it might not be weird? Because what might happen is that there might be some kernel mechanics in place which act exactly like stack. You know, when you have stack, right? The stack of a program, usually only one page is allocated of the stack, even though the stack size is declared to be, for example, 1 megabyte. Now, what happens then is when the program starts to write, like pushes values on the stack, and it suddenly reaches the end of a page, or actually the beginning of it, because the stack goes like towards the lower addresses. And when it reaches the non-existing page, then an exception happens, right? But instead of throwing a signal, the kernel silently handles it and silently allocates that reserved memory. And like a similar stuff might be happening here actually, because why not? So I'm not super surprised that this is happening. The allocations might be done behind the scenes. I guess oh no, but there are some allocations here. BRK is still called, so yeah. I guess BRK is called to... What does it... Do we pass it as an argument anyway? Address. Change the location of program break, which defines the end of a process data segment, blah, blah, blah. Increasing the program break has the effect of allocating memory. So no, this is not the same mechanics. It actually does explicitly call break. It just doesn't do it too frequently for obvious reasons, because we are allocating a rather small amount of memory. So that's fine. I just missed it, yeah. And it's using brcan, it's not using mmap, which is might be, I would say, an important piece of of information. Just to confirm it, I'm going to do this. Yeah, only brks, which is fine. Cool. So memory, Adrian says memory is allocated by BRK and page size pieces, which seems to confirm what we just found out experimentally. So yeah, so that's not the allocation mechanics of the stack, which would work signal-based. Basically, on Windows, by the way, it works the same way as I described on Linux, and by it I mean the stack. Cool. Now let's change it a little, and instead of going, you know, one by one, let's go to maybe not 1 megabyte. Yeah, maybe 1 to 1 megabyte. No, because that would be quite a lot of memory, so I'm going to do, like, I don't know, 60 kilobytes, and I'm going to go by 32, 64, 100, no, 256. Yeah. And now let's see what happens in case in the allocations. It still uses BRK. No way. Compile. Yeah, this is what I was looking for. Basically, my question here was, for what size of allocations does it actually switch from BRK suddenly, which again BRK is used for the standard heap, to just getting the memory directly from the kernel and passing it to the user by the means of mmap. Log 443. No, that's not what I meant, but whatever. So yeah, it uses BRK, 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 and then suddenly it switches to mmap, as you can see here. And for larger allocation, it uses a different way to get the memory of the kernel, which is an interesting piece of information. I would guess it might be useful later for when exploiting stuff, especially that I think that when you do a free from this block, it like from BRK allocated memory, it behaves differently than when you do a free from mmap allocated memory. malloc should be shown by ltrace, not strace. I know that, but I am not tracing malloc. I'm tracing what malloc uses internally, because again, we are analyzing the implementation of the heap and not calls to the heap. Yeah. So, this is fine. Now, I'm actually going to write the sizes here because I want to know where the boundary is. So yeah, let's do maybe this. 10 IP and a new line. Okay, Mormos says that it's 128 times 1 kilobyte, 128 kilobytes. Let's just confirm it. And I'm actually not going to do, or am I going to do this? Yeah, let's just do it. Let's just do this. So again, as you can see, as I told you, standard output is buffered, which let's unbuffer it this way. Yeah. So right, then BRK. As you can see, for like when I'm at 11 kilobytes, it still uses BRK. And the boundary is set to be 128 kilobytes. Let's see if that's true. Yes, it's true. This is 128 kilobytes, and this is the boundary. When we call alloc to it, it actually allocates a little more. It allocates, what is it, 1 page more. Which makes sense, right? Because it does need probably some space for another structure of its own. And anything before that, it actually uses BRK. So this is quite interesting because, again, doing free on it will act in a different way. So, now what I actually know, because I read this paper already, is that when you have a chunk of memory, and this is the interesting part, is the payload is actually the address of the payload. It's actually the memory you requested. The payload is the memory when allocated, you request it as the programmer. And before that is what I told you, is the internal malloc structure, which when we are doing heap exploitation, this is exactly the part which we abuse, and so the other stuff here, because this is a chunk which is allocated, and this is a chunk which has been allocated and then has been freed. And there are some fun stuff here, which I might go and look at in a second. Yeah, so basically, let's start by trying to inspect this. As you can see, there are two fields here. One is called size, and the other is called AMP, which are just flags. It says whether the memory is allocated from an arena, whether it's M-mapped, and whether the previous chunk, which is a chunk which is lying here, is in use. This might be useful for, I don't know, some... Basically, if you have 2-3 chunks of the same of some size, and you need to allocate a chunk which is exactly the size of these 2 chunks added together, then you can just combine them. But to do that efficiently, you probably need this information to be stored here. So yeah, so let's do something like this. I'm going to start by adding another include, that would be std.h, because there's something called uint8t. It's unsigned char, just don't like typing. And yeah, some p as a pointer, and I'm going to allocate 16 bytes of memory, just because. Now, it says that the size of this chunk which I just allocated should be in the size field, which is It's probably, I don't know, it's probably size t. The size of this field is probably size t. Is it explicitly written somewhere here? I'm just going to assume it's size t. Size t is actually 8 bytes on 64 bits and 4 bytes on 32 bits. And if you would read the standard for C or C++, it says that size t is a type which is unsigned and is able to express the biggest possible object in the given environment, which explains why it needs to be 32 or 64 bits. Cool. Now, therefore, what am I going to do? I'm going to do something which is probably undefined behavior, but nobody cares, and it will work. Size is p minus size of size t. And then I'm going to... I'm first going to cast it to as pointer to size t. And then I'm going to do -1. And then I'm going to dereference it. So I'm going basically to read the value of this field. And then I'm going to print it, but as x, llx I think is the correct one. But what I need to do is I need to do something like this. 7 ul, yeah. Since the lowest 3 bits are occupied by the flags, I need to remove it. And the way to remove it is basically to end it with, well, 7. 7 is, you know, is like binary 111, so it just points to the 3 bits, the lowest 3 bits. And then what I do is I negate it, which means these will change to zeros, but whatever was in front, everything in front will be changed to ones. Therefore, when I do end with it, a bitwise end, in the end I get just the size with the lowest bits zeroed. So this should tell me how many bits did I allocate, sorry, how many bytes did I allocate, but it probably will be the chunk size. It won't be the what I requested here. It will be how much is it including the headers and including the padding and alignment and so on. Yeah, 20. 20, let's count, right? So 16, and again, it's hexadecimal, just to be clear. So 16 is actually, you know, hexadecimal 10, obviously. And then we have at least the size here, which is, I'm assuming it's 8 bytes, so that gives us already 18. And then there's this previous size, which previous size is actually a size of a previous chunk. But if the previous chunk is freed, then at the end of it, there is the size of a chunk, because that's how glibc works. Now, I don't know. Then we have 8 byte missing, and I guess the 8 bytes are just alignment for malloc, because why not? It might be aligned to 16 bytes. There are reasons why it could be aligned to 16 bytes, one of which is extensions like CPU extensions like SSE and so on. Some of these require the alignment of the data put in memory to be aligned actually to this size, right? So all the 4 lowest bits of the address are actually zeroed. Otherwise, it won't work. It will throw an exception. So that might be the reason why it's being aligned still to basically this size. Now I'm going to do the same experiment, but with a for loop. And again, what I'm showing is nowhere near heap exploitation yet, but it shows you how you can basically learn about, like, just experiment with the heap. And I didn't get to 3 yet, which is the most interesting part. Okay, and this is incorrect, because, so, when oh, no, it is correct, I just forgot to do this. Yeah. I probably should do I here just to show me. Yeah. No. Yeah. Okay. So again, if I allocate, this doesn't make sense what I'm doing. I'm sorry. I'm kind of tired. It's like 10 p.m. here. Yeah. Now both are hexadecimal, so we can actually learn something from it. As you can see, when it reaches 18, then it's still 20, the chunk size is still 20, but as soon as another byte is requested, then it increased the size by 10, the size of a chunk. Which basically means that I was correct saying that it's aligned to 10. So each chunk will be aligned to 10. Yeah, to 10 as in hexadecimal 10. Which is cool. I guess this already tells me something about how the heap is implemented. Now, what else would be interesting here to check? So we already know the alignment, we already know the boundary where it switches from BRK to mmap. We might want to check the flags here, I guess. Let's check the flags. Let's just... No. Like this. Yeah. Okay, I was thinking of doing a function, but I changed my mind, actually. So first of all, sorry, which flag is which? Okay, so P is previous chunk is in use. So let's just do P, or small p. Now I'm going to do the same thing, but in a different way, just because I can. So instead of writing this, I'm going to do... what is the second one? So M and M. And now this obviously returns either 0 or 2. And there is a super funny and fast way in C to actually change this to return from 0 and N, return always 0 and 1, and that's by adding 2 exclamation marks at the beginning. Now, these 2 exclamation marks translated to assembly probably mean there will be 2 compares and 2 jumps, but yeah, who cares? And the third one, I'm just going to do the same way here. It's obviously 4 and A. Okay. So again, this is the same thing, I just written differently. Just in case you like tricks like this. What did I mess up? No, seriously. 15, line 15. This is full. This is cool. Expected expression. I'm really tired if I'm making mistakes like this. Oh, I know what I messed up here. Here should be C. Because, or should it be? Yeah, it should be C. Okay. Right, it's not Python. It's one of the mistakes you make if you're programming in a couple of different languages and you switch from them. Like, I don't know, I programmed today in Python and now I'm programming in C. And in Python you can usually leave a comma here, and you usually should leave the comma here. But in C you shouldn't, so that's why you make mistakes like that. Cool. So as you can see, it says that the previous chunk is in use. Well, that's pretty obvious because the previous chunk to this is actually this chunk, and I'm pretty sure it is in use. M is not set because it's not an mmap chunk. So yeah, it's BRK chunk, so that's true. And A is also not set, that means it's arena allocated, which means that, what does it mean? So arenas are basically, I guess I should let you read the document, but in the end it's like this. When you have multi-threading, right, you probably do want to have different heap regions and different heaps for each thread, if possible, because if you don't, that means that you will be constantly doing mutex logs, muti logs on malloc and on free, and you don't want it. If you have multi-threading, you probably just would be happy to have each thread having its own heap, and therefore each own malloc and free without any mutexes. That will be just faster, because one thread when allocated will not wait for another thread, it will just like use its own memory area. So arenas are related to that. I'm not going to go into the details, but I guess it would make a fun CTF challenge to incorporate arenas as well. Cool. So so this is fine. Now what I'm going to do is I'm going again to increase. Let's go to the 128 byte boundary, and let's see if the flag, the M flag, right, changes suddenly from lower M, which means not set, to a capital M, which means mallocked. And now I'm going to do this, and I'm going to do 256 because why not? See, boom, yeah. And again, as you can see, this flag is suddenly being set for as soon as we reach the 128 kilobyte boundary, then it sets this flag saying that yeah, this is actually a map, this is not barcade. And it also says that there is no previous chunk, or the previous chunk is not in use, which is quite interesting. Which one is it? Maybe it's both actually, or maybe the flag is ignored in case it's mapped. It's worth reading into. Yeah. So okay, so we learned something about the header. Now the more interesting part is which will be when we are starting to free stuff. So I'm going to, I don't know, just delete it or maybe comment it out. And the first question is that if I do alloc, 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 and then free, and then alloc again of the same size, will it reuse the block I just freed? Because if it does, that means during exploitation you can totally abuse the fact, just to, for example, free some memory and then allocate it again in some other region of a program, and then have a dangling pointer, for example, there. So yeah, maybe before I jump there, is one thing I should mention at the beginning, which I didn't, I'm sorry about that, is that heap exploitation is actually not one bug which you exploit, like format string, right? It's just one bug, format string, and you exploit the format string. And there are like a couple of cases, how do you exploit, but it's usually the one and only bug called format string. Now in heap, there are several bugs. First one is, and the easiest one by all means, is so-called use after free, which means you allocate some object on the heap, and then there are like a couple of pointers pointing to that object, and you cause the program to free the object, but the pointers are not updated and are still pointed to that area of memory, still thinking the memory is alive. And then you allocate some memory in the same region, or force the program to do it, and assuming you tell it that it's a different object now, and I can actually control, you as an attacker can control most of that object, then you can cause through the dangling pointers to access it as it would have a different type, and all hell breaks loose depending on what kind of objects we are talking about. This is usually the most easy to exploit. It's called use after free. Now the other one is, which is a little harder to exploit, is double free, which means you free some area of memory, and then you cause the program to free it again, even though it was already freed. Maybe in between, and usually that's the case, you are able to interact with the memory and, for example, set it to whatever, like, allocated through a different branch in the program, put some stuff there, and then cause to call a free on that area of memory again, and it respects, for example, some size of a chunk which you could totally mess up, and therefore in the end get some execution, some code execution. Though there's a long way, but I'll get to it, I guess, not today but later. And then there is the classical buffer overflow, which means you do have a chunk of memory and you overflow it. And what do you overflow? What do you overwrite here? Well, obviously you overwrite this structure, right? And you also overwrite the freed chunk version of this structure, which means, and there are some pointers here, and you can usually get a so-called write what were condition. But that's also something I will need to follow up later on. Yeah, so like these are like three typical classes of bugs when talking about heap exploitation. So it's just not one bug, it's like a class of bugs. And To exploit each of them, you usually do need to understand how the heap behaves when allocating certain sizes, when deallocating. So this is why I'm doing these experiments to be able to, in case of exploitation, actually be able to set the chunks to my liking on the heap, and therefore be able to overwrite what I want and to free what I want and so on. Okay, so the last thing I'm going to do today is I'm going to see if it actually does allocate things which I just freed, like return the same addresses. So let's do it like this. I'm going to allocate, let's say, 16 bytes of memory, because why not? And I'm going to free it here, though I'm not. Yeah, let's do this. And so I allocated it, then I allocate it again. Okay, I'm going to mark it as P here. And now I'm going to free P. Yeah, that's fine. And now I'm going to allocate some other blocks of memory. And what I want to find out is this address, which I've written out here, will it appear somewhere here in one of these allocations after I free it? Let's see. And what do we have here? So this is like, yeah, this is what I freed, right? And it appears here, like the first allocation of the same size after the free, and it already appears here, which means that probably when I freed it, there was some linked list, and the chunk was added to the linked list, and as soon as I requested to allocate a similar size of memory, then this linked list was found, and it was checked whether there is some chunk here, and was passed here, without even going through the heap itself, right? And usually what I would imagine is happening is that there isn't a single linked list, but these are more like buckets, or like a hash list, if you will. So they're like sizes, for example, from like 0 bytes to I don't know, 32. Then there is like linked list 1, and from like 33 to I don't know, 64, there is linked list 2, and so on. And another interesting part, which I'm going to probably do off stream, is finding out what buckets are there, and therefore also if I can do allocations of different sizes and free them, like what can I expect when doing allocations of similarly yet different sizes to which allocation which I actually get, which address of memory chunk will I get. And this is quite interesting and quite important when you're doing exploitation. That's why it makes sense to do these kind of experiments. Cool, so what I'm going to do here is I'm going to actually do I'm going to do something like this. Interact okay. And I'm going to allocate here a to I, which is ASCII string to integer argv of 1. Yeah, so I'll pass the size as an argument, and I see if it actually returns the same address it just freed here. So obviously if I do 16, right, it will, like this is the same address as you can see. Now let's see if I do 15, the same address, 13, sorry, 8 still has the same address. You can see the offset, right? Even though everything else changes, I'm just looking at the offset. But yeah, but this is the same anyway. 0. So yeah, so this is the same bucket, obviously. Now I did 18, and it also allocated the same area of memory, because I guess I can expect it to go up to 24 at least, because that was the size of a chunk. Yeah, and when I did 25, this is a different address. So, but that's not the bucket. That's the was the size of the chunk. The chunk was just too small to be able to be used for allocation of 25 bytes. Cool. So the follow-up from here would be, first of all, try to determine the bucket sizes if there are any buckets, or maybe it's just like a single linked list, I don't know. Or some other structure, it doesn't have to be a linked list, right? It could be some kind of a tree instead of a linked, of a bucketed linked list. That would be one thing I would do, and the other thing, which I'm going to also do off stream, is probably start playing with these fields, like take a look at these fields. And another thing which I will probably do is what I would do, I might write a blog post about it actually, is like write a debugger script, which I would pass it a chunk address, right? And just using the size field, it would walk through the heap and tell me of all the things which are there, like all the chunk pieces which are there, because it should be doable just using the size field. Whoa, I can actually select text on this. I thought these were images. I am positively surprised. I need to take it how it's done. Cool. So I will actually finish up today. Again, I didn't really reach the exploitation as expected. I might do it in the next stream or in 2 weeks or so on. If you have any ideas for, basically any ideas for the topics of my live streams, just put them in the comments under this video, especially when it will appear on YouTube. If you have any questions right now, then feel free to ask, and I'll try to answer them. I don't know, I'll be here, let's say, another 5 minutes. And that's it for today. If you were late to the show, then I will be posting the links, all the links that I gave you today under the video description, or in the video description. So that's it. Okay, so I'm going to, I guess, copy paste the links and wait if there are any questions, and if not, then we wrap it up. And I'm going to play some music in the meantime. What's the music from? The music is from, it's a game called, what was it? It's not Frozen Synapse, it's Frozen Cortex. And it was made by Nervous Test Pilot, which agreed to actually let me use it on my stream, which I'm really happy about. Yeah, this is the game. He actually makes really great music, I really like it. Anything on Windows kernel fuzzing? I mean, if that's an idea for a stream, then please be sure to put it in the comments under the video. As for anything I can say on it is, well, I can say that it works, but it's a complicated topic, I guess. Usually you have to have a virtual machine, and you have to either fuzz the syscalls, like call syscalls with random arguments, not really random, they have to be somewhat related. Yeah, it's a complicated topic. It's actually a good idea to maybe chat about it on some of the next streams if you like the general idea of the topic. Maybe you could do the CTF challenge leaked in the CIA leak. So if I remember correctly, that was a malware-related CTF challenge, but I didn't really look into it. What is it really about? So I don't know if that was a real CTF challenge or was it something else. But I'll take a look. That sounds interesting. Cool. So I guess if there are no more questions, then yeah, if you have any ideas on what can I talk about next, or should I like continue on the heap exploitation basics, then totally let me know and I'll do it. I'd like to thank again KrzaQ for staying late, for being today and helping me out, and thank you for coming. And I'll be probably on the chat for a couple of more minutes if you have any follow-up questions. Okay, there are 2 more questions. Any news about my book? No, not yet, and it will be late 2018 probably. Or if you're asking about the reverse engineering book, which I co-authored and co-edited, then that the publisher decided to postpone the decision whether to publish it to the end of the year, so which means it's not coming yet, and it might not be coming ever. Yeah, sorry, that's not good news, I know about it. Sandbox escape, that's also a good topic. That's a really good topic for another live stream actually, so please put it in the comments under the video once it shows on YouTube, because that is a good topic for a video. Yeah, I'm sad as well for the book. Yeah. Okay, so that's it for today, and thank you for coming, and let me know what you think about the topics and the way I present in the comments as well. I kind of realize that my Polish streams are currently better, mostly because I tend to finish the topic I'm starting, and yeah, and it's also the last, I think, 2 or 3 streams here was about me showing how to learn something, and that's not well, not really what you might be interested in. Let me know that as well in the comments, and I'll try to change the topics basically and like run them up in a way that you would like. So that's it. Thank you for coming, and see you next week. Bye bye.